Hey, it's Brandon from STEM Tutoring, and today we're going to try to make sense of negative exponents. In the last video, we left off with something like this, where we had 2 to the negative third power, and based on our reasoning, we found that it was exactly equal to 1 divided by 2 to the positive third power. And in this video, we want to try to make sense of that. In order to understand this, let's start off with our positive exponents and then slowly work our way down. So if you look on the left side right here, we have 2 to the fourth power, which is equal to 16. And then we have 2 to the third, which is equal to 8, 2 to the second, 2 to the first, etc. Now, as we move down this list on the left-hand side, we're basically subtracting 1 from the exponent. So 4 to 3, then 3 to 2, then 2 to 1. And as we subtract 1 from the exponent, what is happening to our actual number? Well, if we have start off at 16, and then to get to 8, we're clearly dividing by 2. So, right, dividing by 2. And then to get to from 8 to 4, we're dividing by 2 again. And then to get from 4 to 2, we're dividing by 2 again. So every time that we decrease our exponent by 1 on the left, we're dividing our output number by 2. And we can continue this pattern. So if we wanted to plug in 2 to the 0th power, so again, just continuing our pattern here on the left, and then on the right, what would we expect to happen? Well, we'd expect to have 2 divided by 2, which would give us 1. And this is kind of interesting because this explains why raising something to the 0th power is actually equal to 1. If we just blindly follow this pattern, then it makes perfect sense. But we can go a little bit further. So we can just continue this pattern indefinitely. And then if we do that, we actually start to see some negative exponents. So if we start off with 2 to the negative first power, again, we're just continuing our pattern of subtracting 1 from our exponent on the left, so going from 0 to negative 1 now. Well, on the right, we would expect to continue the pattern. So 1 divided by 2, what does that equal to? 1/2. And we could keep going as well. So we could do it again. So if we get 2 to the negative 2 power, so again, just subtracting 1 from our exponent on the left, and then on the right, we'll do 1/2 divided by 2, which should be 1/4. And then if we continue it again, there's no end to this. We can just keep going forever in the negative direction. And if we do that, in this case, we'll have 1/4 divided by 2, which is 1/8. So this hopefully gives an idea of why negative exponents actually make sense. So hopefully this explains why negative exponents make sense. When we're taking positive exponents, 2 to the 5th power, for example, then we're starting off at 1, and then we're multiplying that by 2 5 times. However, when we're taking the negative exponent, so like 2 to the negative 5th, for example, then we should in some sense be doing the opposite, because a negative 5 is the opposite of 5. So instead of multiplying, we will do the opposite of that and divide. So we'll start off with 1 again, but this time divide by 2 5 times, which is why we end up with continuing this pattern, 1 divided by 2 to the positive 5th power, if you're just looking at the denominator. And by the way, this could be generalized to any base and any exponent. So the general formula is x to the negative n power is equal to 1 divided by x to the positive n power. The only number we can't have for the base is 0, because that would imply division by 0, which is not allowed. So these are just some common negative exponents down here and what they equal. And if we actually just accept this definition of negative exponents, then everything else with exponent properties actually fall into place. So it might seem weird to think of negative exponents, but it actually does make sense to talk about them. So I hope that made negative exponents make more sense, and be sure to stick around for our later exponent properties in this series. See ya.